So today's class just so last time we had this commutative property. So for condition operators, whether they commute or not. So in this, so we are going to continue with that and see the properties of these operators in some general sense, where we can arrive at orthogonality conditions or orthonormality conditions. So that's it. So what we are going to, so we don't, so for example, so we assume, for example, we assume that x and px may commute, do not commute. Failure of x and px do not commute is somehow connected with uncertainty relation. That the simultaneous measurement of commutation two observables in quantum mechanics they would commute. So it's articulated or it's stated as it's sort of uncertainty relationship. So given any dynamical variable, given any dynamical variable A, the question is how do we find and characterize those values, those particular values or particular states of the system in which they will have a definite value. So the question is how can so given the dynamical value, the point is how do we find and characterize those states of the system? Psi A eigenstates which will have eigenvalues. So the question is, since this हमारे पास जो states हैं, it can not have one values because we are interested in the probabilities or we are interested in the expectation values. So it may not take one value. The question is how can you characterize those particular states of the system which they will have not one value but different values. So this is the question. So whether we can characterize them or not. If we can characterize them, how? We can assign values to those states which will have a definite value once we are going to measure a system. So if we denote them in terms of some primes, symbol A prime, so it's a numerical value of some dynamical value. And which distributes it from some physical state A. So it's a dynamical variable and it's some physical state A. So the question is, if we measure A for a large number of separate systems or n-systems, and all of these separate states are some replica of psi, जो हमारे पास state psi है, उसका evolution, psi का evolution under various conditions, or it's going to. So it's A is large number of separate systems, so evolve with the same field function psi, The question is, what values will it have for having a sharp value of psi? So in the same of that Gaussian thing, so what's the value? It will have some sharp, precise value, which will be a particular value. So it will have that sharp, that pillbox, the sharp thing. But if our measurement about that variable is sharp in that sense, the corresponding variables will not be that sharp, which will, if it doesn't have the spread, wave spread, so that's it. So that will give us the sharp or the different value. But we are not talking simultaneously कि इसका जो simultaneous variable का how we can pin it down. We are trying to address basically this question. How we can characterize those particular values of the system in which they will have a different value. Now we are coming back to our definition of how we define probability, how we arrive at expectation values. And we had a statistical way how we define variance, कैसे हम define करते हैं. So variance, we try to define variance as f of a is f of a prime, where a is equal to a prime. So if we define variance of a function vis-a-vis a, so we have defined a as a physical state, and we have defined a prime as a physical, so dimensional variable which will correspond to a, which are large number of separate systems or evolved states which are represented by psi. So we can have a correspondence of this variance, it corresponds to this function, or expectation value of a prime, which is basically this average of the closely evolved system, or this average value, it's the value of this a which we are going to have. Or if we have, since we are interested in the square, we are interested in the square of the variance, we are interested in the square of the variance, we assume that this expectation value e square is equal to a prime square is equal to e square. So square of this is equal to the mean of square, if you assume. So if you assume that way, this means जो हमारे पास will have a vanishing variance. Delta A square means mean of the square, when the square of the mean will not come out to be some quantity. It will be definitely zero. Or so vanishing of the variance can be written as a minus b along some mean value should be equal to a square minus this thing. That's it. So now the point is that so we were yesterday talking of Hermitian operators, when the condition of that when they will commute these Hermitian. So that condition, if it's applicable here, that we are going to observe these variables for a given state, it will correspond to different eigenstate, this thing. So if we get it, if it is quadratically integrable, then for a special state psi, what I should say, For a state where this A will become A prime, sharp correspond to that sharp value, or address this question of whether it will have some different value. But it will correspond to a O1 condition correspond to where these Hermitian operators they will commute. Then only we can pin or fix that particular value. So it will be sort of square integrable, or जो हमारा expectation value आएगा, the way we have been calculating the expectation value. Expectation value कैसे calculate करें? We took side. We said the sandwich between the mean or how to calculate the variance and psi star. So this is the mean. We have psi star and we have this A minus A prime square psi. If it's in function space. So if they will commute this A minus A square, this A minus A square. So it will come out to 0 for commuting thing if they will commute. And operator AB, operator हमारे पास है operator AB dynamical value is Hermitian A prime and A prime is there. And the last equation will become the last equation it will have the form so it will become like this. So we have integral of A minus. If we write it like this, A minus B square, we can write it like psi star A minus A prime psi of B star. Further, you can say it if that's equal to 0 because we are commuting, because we have to pin down a different value. If it's such a different value, then these expectation values or the probability which we are calculating. So if you calculate the integral, if you take one of them, it will come out to be 0. Then from this, you can say that A minus A prime side is equal to 1, it's 0, so it will come out to be psi square or psi star it's equal to psi square if you are equal to 0. It means A psi is equal to A prime psi. So we have arrived at what we want. So for a particular value of this dynamical variable, it will have some different state psi. That's the thing which we have to calculate. Means that जो हमने किया है what we have done, we have a quadratically integral function satisfies this function. So a quadratically integral satisfies this function. This is an eigenfunction of A, and a real number A prime. So we are because we yesterday also said that Hermitian operators they will have correspond to for commuting operators the value should be real. So if it is like that, हमारे पास ये है satisfied eigenfunctions of A and the real numbers A, then A prime, the A prime is the corresponding eigenvalue. Interesting. So for the previous question, for this integral function of satisfied eigenfunction A, for a function eigenfunction A, there should correspond a real number A prime. Is that corresponding? For a given eigenfunction, there will be a corresponding eigenvalue A for a given state psi in that sense. So this is this. So all eigenvalues will form of A will belong to that spectrum of this. Now the thing is, if it's momentum, it's or position values, you can also calculate the expectation values for momentum d3p and vice versa and relate the two. How we can relate in the position space as well as momentum space for a given eigenfunction. What's the corresponding eigenvalue for a given state? We can do the same exercise for position, but the thing is, in position's momentum, you have to go from phi space to phi space to psi space to psi space. It's in R to phi space. So here it will be A minus A prime for this thing. It will be phi of A minus A prime. This phi star phi. So phi B3. Now we can, if you want to make a relation, then we can also go from side to phi minus side line for position and momentum space. Yes. Now we are going to do one further exercise which will show whether the reality of eigenvalues, whether the reality of eigenvalues whether the reality of eigenvalues, the reality of eigenvalues of Hermitian operators needs no proof. In the sense that so we have to retrieve there are conditions of orthogonality here or come. So I'll retrieve for come. So we are basically trying to see when two eigen हमारे पास जो हर्मिटियन ऑपरेटर है जो हमारे पास फॉरवर्ड से तो हमारे पास हर्मिटियन ऑपरेटर्स हम कम्यूट हो रहे हैं, ठीक है. फॉर अ पर्टिकुलर आइगन स्टेट देयर इज अ पर्टिकुलर आइगन वैल्यू लाइक दिस. हमारे पास एक स्टेट है दिस कंडीशन की हम एक्सपेक्टेशन वैल्यू निकालते हैं, ठीक है. हमारा काम है कि फॉर ए पर्टिकुलर आइगन फंक्शन देयर इज अ पर्टिकुलर आइगन स्टेट निकालना है हमारे पास, ठीक है. सो इफ वी हैव दैट कंडीशन दिस मींस दैट वी हैव अ डिफरेंट वैल्यू ऑफ दैट वेरिएबल मेजरमेंट्स का. दिस मींस जो हम इन दैट सेंस देखिए अगर किसी चीज़ का मेजरमेंट डेफिनेट लेंगे तो उसका साइमल्टेनियस वेरिएबल होगा दैट विल बिकम इंडेफिनिट बाय अनसर्टेनिटी रिलेशनशिप, ठीक है। सो बट वी विल ट्राई टू से हाउ कैन हैव when can a definite value to a given observation. This is our job. So in the sense we have done that bit of exercise. Now we are going to do the same thing if we first हमने कहा था हम कर सकते हैं कि नहीं कर सकते, अब आपने यहाँ पर किया है। Now the question is if we consider two eigenfunctions of A psi 1 psi 2 corresponding to two values. Now हमने कहा था whether we can do it or not, we have shown we can do it for integrable functions. मगर अगर हमारे पास दो साइड फंक्शंस है psi 1 and psi 2, यहाँ पर है psi star with c. Now if you are going to take two eigenstates corresponding to two functions of A. So at the end we said there will not be one value, there will be a spectrum of values which will correspond to that given state, ठीक है। अब अगर हमारे पास दो होंगे फॉर एग्जांपल where A psi 1, तो यहाँ से हमें पता है कि A यहाँ से reduce just substitute A psi is equal to A prime psi for a particular eigenfunction we have a particular eigenstate. अब हमारे पास अगर दो eigenfunctions हैं which correspond to a given state, तो we change psi and psi star, तो हम will have two forms. एक में होगा A psi 1 is equal to A1 prime psi 2 and A psi 2 will take दो, एक में psi 1 psi 2 इसमें psi 2 will have this. अब what we are going to do? So we are going to do a bit of algebra here, multiplying जो है ना इक्वेशन इसको लेफ्ट अगर इसको 1 रखेंगे इक्वेशन 2 रखेंगे मल्टीप्लाइंग इक्वेशन 1 बाय psi 2 स्टार, पहले इसको psi 2 स्टार से मल्टीप्लाई करेंगे, इसको psi 2 स्टार से मल्टीप्लाई करेंगे, psi 2 स्टार से मल्टीप्लाई करेंगे एंड देन इसका कॉम्प्लेक्स कंजुगेट एंड मल्टीप्लाइंग दिस इक्वेशन बाय इसका कॉम्प्लेक्स कंजुगेट लेंगे एंड मल्टीप्लाइंग इट बाय साइन, ठीक है। इसको लेंगे तो पहले इसका इक्वेशन का कॉम्प्लेक्स कंजुगेट करेंगे मल्टीप्लाई बाय साइन स्टार एंड इसका एंड नाउ सब्ट्रैक्ट if you subtract that so it will be equal to तो ये जो इसमें ये 0 आएगा so it will come out में इंटीग्रेट करके इसको आप यहाँ करेंगे A1 है ये A2 है it will be A1 minus A2 star whereas according to the Hermitian property sin star अब ये हमारे पास है A1 minus A2, this is sin 1, this is sin 2 star sin, it is equal to 0, so it's equal to पिछले वाले में हमारे पास we only had sin psi, यहाँ हमारे पास है sin and sin, तो हमने थोड़ा सा इसको एक्सरसाइज किया एट द एंड जो हमारी जो इंटीग्रेबिलिटी कंडीशन है इट विल कम आउट लाइक दिस। अब हमारे पास sin टू sin है इसको 0, अब इसमें अगर ये वाला 0 है आएगा जस्ट इसको डिवाइड करो यहाँ से इट मींस इधर sin 2 is equal to sin और A2 prime ये वाला A2 prime is equal to A2 star is equal to A1 और since A2 star is equal to A1, this means A1 is equal to A1 star. ठीक है, which demonstrates, हमको क्या demonstrate करना है, which demonstrates that eigenstates are all real. Eigenstates are all real. तो कल हमने if you remember, so we said कि जो Hermitian operators हैं, they are commuting operators. क्या है? And जब आप commuting operators हैं, they are real. They are real. अब जो quantum mechanical variables है, if you want to have a definite value of a given eigenvalue to a different eigenstate, so it will also be real. ठीक है? So जो and what we are going to observe, it should have some real value. ठीक है? So this is what we have to do. That for all eigenstates, they can have real values as an exercise. So this means that और इसमें मसला ये है, there's another thing. For example, this means अगर हमने इधर इसको 0 दिया तभी तो हमारा A1 आएगा A2 के बराबर 0. अब हम इसको 0 रखेंगे, ठीक है? Integral of GTR 0. This means integral of psi 2 star psi 1 BTR is 0. So यहाँ से हमने कहा कि wave functions corresponding to two different eigenvalues. ये ना psi 2 का है psi 2 for it. So if you don't, अगर हम इसको अपना लेंगे, so it's A1. So for two different psi 2, for two different psi 1 के लिए for two different districts, इसका A1 का A1 प्राइम आएगा, A2 का A2 प्राइम आएगा, और इसका है ना psi 1, इसका psi 2. ये कह रहा है कि two eigen ये है wave function psi 1 and psi 2. इसका वैल्यू 0 है. इसका मतलब क्या है? इसका मतलब है eigen functions corresponding to different eigenvalues और orthogonal, है ना? Orthogonal मतलब क्या होगा? cos 0 is equal to 1, cos 90 is equal to 0, है ना? Orthogonality condition. They are perpendicular. एक जा रहा है. So this means जो अगर हमारे पास sin are same, ठीक है? So this means you will have this condition. But if sin and psi star are different states, ठीक है? So they will commute or they will have this known as orthogonality condition. ठीक है? This known as orthogonality. हाँ.
अगर सेम है तो commutative कर दो.
नहीं, commuting means that for example x and p, the product क्या है? X means, so this is known as commuting. If you simultaneously measure these two variables, this is commuting. Orthogonal होगा for example x और x अगर perpendicular होगा, जैसे x dot x is equal to cos 0 1, but if x dot x are perpendicular, x perpendicular, so it will be 0. एक component इसमें, एक component for the same value. अब यहाँ हम normally psi ले लेते हैं, ठीक है? psi normally, क्योंकि अब हमने चेंज किया, हमने psi नहीं लिया, हमने लिया psi 2. This means एक psi है, एक psi 2. psi 2 is perpendicular to psi 2. ठीक है? अब ये है कि so this is what so from this we conclude they are orthogonal. अब ये हमने कहा कि ये वाली कंडीशन अगर सेम स्टेट्स हो गए sin psi star we can trivially satisfy them. बट अगर हमने psi को डिफरेंट लिया psi 1 and still the equation will be satisfied. अब इसमें दो conditions आ सकती हैं, whether they are orthogonal or not. If psi 1 and psi 2 are different state, still the equation, then we say that इसमें तो ये simple है, this is going to this. अब इसमें जब psi 1 and psi 2 are different, इसमें जो equation हमारे पास आई थी यहाँ पर sin a1 minus a2, इसमें ये तो zero है, इसमें ये है कि whether psi 1 and psi 2 are दो solution. If psi 1 is equal to psi 2, तो we'll have a trivial case, ठीक है हमारा. But if psi 1 is not psi 2, psi 1 and psi 2 are different, तब orthogonality condition आ सकती है, ठीक है. This is the thing. And we can say that अब इसी को कहते हैं all n eigenvectors, eigenfunctions belong to an eigenvalue A prime, all eigenfunctions belong to the eigenvalues A prime must be linearly independent. इसको कहते हैं linearly. है ना? We are basically just how A and A prime are related for a particular value psi. That's A prime psi is equal to A psi. Simplest case. But if psi and psi prime are not same, they are different, then still we'll get an orthogonality conditions if psi and psi are. So if that is the case, this means all for a given eigenfunction there is a given eigenstate. For trivial case it's okay. For if psi 1 not equal to psi 2, so they correspond to the orthogonality condition. This means they are linearly independent. Linearly independent means they could have linear dependence. You know, आपने कोई भी condition alpha 1 a1 plus alpha 2 a2 plus is only linear case. If alpha 1 is equal to alpha 2 is equal to which is 0. Okay? This is linearly independent. If alpha 1 and alpha 2 they are not 0, then linear dependence. Linear dependence means no psi and psi are not related to each other. Okay? They are independent in that sense. This means that one of them, अगर हमारे पास बहुत सारी spectrum of these states है, psi and psi prime के बहुत सी values हैं. अब हमने कहा some of them are orthogonal. So orthogonal state में भी one of the states among the general states, some of them may be orthogonal. Not all of them may be orthogonal. क्योंकि हमने ये trivial states में a psi is equal to a psi. For a given eigenfunction, there is a given eigenstate. अब कौन सा eigenfunction है? There will be class of eigenfunctions which will correspond to given eigenstate. उसमें भी if psi and psi are not same, they may correspond to the orthogonality conditions. ठीक है? वो ये कह रहा है कि this means that some of them may be expressed as the some of them, not all, as a linear combination of all. Or any two of them may or may not be orthogonal. This is the point we are going to see. हाँ, अब इसमें यह है कि how we can construct general states, eigenstates. इसको कहते हैं Gram next class, Gram-Schmidt condition. How we can construct given states which will be orthogonal or as well as this thing. And eigenfunctions that are orthogonal and belong to the same state. So this is the procedure. Okay.